So, uh, hello. I'm going to present you my topic, design and implementation of optimized arithmetic logic unit using digital logic circuits. Firstly, will have an introduction regarding it. What is an ALU? ALU is a fundamental component of uh, computers which of a central processing unit. It is responsible for arithmetic and logical operations like arithmetic operations like addition, subtraction, and logical are and or etc. So why it is important? So here in a computer we need a computational brain. It works as a computational brain for a software. Sorry, for a processor. So we required it for addition, subtraction, logic gate usage and all. Uh, Here essential for designing microcontroller. Yes, it is essential for designing microcontrollers embedded system. We need an optimized version of it because we need a fast-paced processor, right? As we are using mostly 64-bit is a fast pace compared to the earlier generation. This is a simple logic diagram how an ALU work. We will take two inputs, then we will control them using selecting line of a multiplexer. We'll go on further at Deeds to look at the proper ALU and get the out. The objective of this study, the primary objective of the study is to make a effective and optimized ALU using fundamental digital logic units, logic gates, sorry. So main aim would be reducing the complexity of the circuit and delay as there is addition, subtraction, all the process going on, there will be delay and how we can optimize it and make it less delay. We will see it. Secondary, we will analyze in a hardware form. It uses 2FP and other. I will show later. Scope of the study. We are going to build 4-bit or 8-bit. I am going to build a 8-bit ALU. And what are the, as we talked, arithmetic and logical units. Here in arithmetic unit, it does addition, subtraction, increment, decrement, logic. In logical part, it does AND, OR, XOR, comparison, greater, and many more. What are the tools? For example, Logism, Tinkercad, Deeds-DcS, and all. We can use to make them on in a laptop if we don't want to make in a hardware way. These are the basic components and OR gate, XOR, NAND, NOR. Multiplexer is much needed. Full adder, subtractor. Methodology we will discuss later. Parameters, key parameters. Okay, firstly we need to count how many gate do we require. Then we need to optimize the propagation delay, for which adder rate will be less delay compared to the other, like power consumption. Yes, it is one of the important reasons. And scalability, in how much place it won't take too much space in a laptop, or else it will be larger, or you know. Then okay, firstly we are going to come out types of adder. There are mainly 4 types we are going to discuss. First is ripple carry adder. Here, ripple carry adder, mostly we all have learned about it. It is a chain full of adders which gives the output. At last, we get the carry out. As we know, it is the worst for delay timing. It takes a linear with respect to the number of bit. As many bits as the bit number of bit will increase, the time will also increase linearly. So it is a very time consuming process. For 8-bit, 64-bit, it will take a huge time. Advantage, it has simple design. It is very easy to design, fewer hardware resources. Yes, it required 2-3 gates only. I mean, we need to use the gates again and again. And disadvantage, yes, it is the slowest among all, as we have talked. Carry look ahead adder, CLA. It has working principle which generate and propagates carry. It will generate a carry using this formula and a propagation formula, and we'll get the next carry. What will be the next carry by this formula? So it will decrease the delay timing. So our delay will be in a logarithm form, which is much faster than the earlier RCA. So advantage is faster timing, but disadvantage are it is complex and power consumption is high. So this is CSA, carry save adder. Uh, it uses multiple operands to get a propagated carry, and then we will add both the sums like that are later added, which is useful, but it has a disadvantage like not ideal, because we are going to use one more adder again which is faster than it. So why should we use two adders? Normally it is not suggested to use. Advantages: partial product addition, yes, and parallel carry handling, yes, it has a parallel carry handling. Best among all, but costly. Cogglestone adder. It is a parallel prefix adder, which works on a tree structure logic. It builds carry using a graphical form and gets carry in a fraction of seconds. I mean microseconds, nanoseconds. Fastest among all. Advantage: it is fastener, fastest due to it do not have too much logic. It just makes a graph, a future graph, and get a carry adder and add all them. Ideal for high performance, yes. Complex wiring and large area scalability and high power consumption means. So here it is, which should be used. Like if you want speed, go with the cobblestone, which is fastest, and carry look ahead. While carry saver and are slow and medium. So the most moderate one is cobblestone. I mean moderate in the moderate, sorry, complex one, complexity wise. While rebel carry is the simplest one, and the carry look ahead and carry saver are moderate one. Best use. Yes, a ripple carry can be used in small ALU like we have used it out in our ALU, 8-bit ALU, 4-bit ALU. Carry look ahead for fast adding purpose if we need to increase the speed of ALU. High speed multiplier. Yes, carry saver is used in high speed multiplier, and cobblestone are just used in a very larger ALU. So because as it is very costly, so here we conclude that carry look ahead mostly it is suggested to all because it has a balance of speed and complexity. We can use cobblestone when we require a higher speed and we don't have limitations like area wise or power wise. Not often the repel carry and carry saver are used. Oh, sorry. What is use of multiplexer? Here we are going to use multiplexer to select what command we need to do. Like for 00 we are going to do addition, for 001 we are going to do subtraction, like that, using selecting lines. We all know. This is how it works. Here we have taken the example of 4-bit multiplexer. S1 S00 add subtraction. I already explained it. Working of logic gates in ALU. Logic gates are it only stands in its name, arithmetic and logical units. So there should be some logical things. For example, logical and OR has been used here, not XOR. So we already know regarding this, and we are going to further see in a Deeds of 8-bit ALU. Okay, usage of shift and rotate operation in the ALU. Okay, let us directly go to the shift operation. We have a logical shift. Here we will shift a number from towards the left. Like see, 100 1011 we are just pushing it to the left, and the one at the end is disappeared. Just look at and adding the 0. As we push all the number towards the left, we will add 0 at the starting. Similarly for the right one, we will push all the number towards the right. Just look at here, pushing towards the right and adding 0 at the end, and whatever the first bit was here it just disappears. Arithmetic shift right mostly used. It has a different scenario. When it is a positive number, it won't add 1, but when it is a negative number, it will add 1 at the end. Uh, because we get 2's complement using this. So just look at it, this is a negative number. We are just shifting it towards the right, and I will show you that later on, not too much to know right now. Rotate L, ROL, okay. ROL, okay, rotate left one. Okay, yes, sorry. Um, it will place the first bit toward the leftmost bit in the number and towards the right at the end. Okay, just look at here. It will push this bit towards the end. From here it goes to here, and opposite for ROR, it will it will take the rightmost bit to the first position. Like here, it will place it to the front. Simple. Power consumption techniques. It is power consumption. We know we need a high mobile. In mobile phone, we use processor which uses ALU for sure, and we also need a good battery life of it. So we need to make we need to do some power optimization to make it so that it can use less power. We need a high performance with less heat and good power backup. So power optimization is necessary. There are two types of power optimization: dynamic power and static power. Dynamic is caused by charging and discharging of capacitive loads during switching, while static is present. It is present in all the ideal circuit mostly. It depends on the switching frequency and supply voltage, while static power is due to leakage current. Okay. Mostly dynamically is used always. Gating, clock gating, as we know, the clock signal. Here is the idea that the clock signal to use unused, giving disable the clock signal for the unused part of the ALU. matlab, for I mean suppose we are not using any logical gate right now, so we will disable the clock signal for them, and only for the adder or subtractor which we are using right now, we will make the clock signal on only at that time, so that we don't use too much power on all the components of the ALU, and we don't need to go in the depth of all this. This is the best technique. Best is the power getting, but you can look at it. We don't need to go this deep. If you want to use power save, if you want max power saving, then power getting is the best. While if you want a, but it has a medium, I mean area impact, and it has very high complexity. But mostly we will use a clock gating because good amount of power save, less area impact, and complexity is medium, not too much high. So we can use it. Area optimization. Yes, we need a area optimization because it should fit in our mobile phone, and also we need it. We need to make it in a smaller, as minimized as possible. So these are the technique using K-maps to reduce the gate, using universal gate like NAND and NOR, using share module, using only the single module for addition, subtraction again and again, and etc. We can use that. Scalability. The here if we want to do an 8-bit addition, but we are having 4-bit ALU, so how can we do that? So lining this 4-bit ALU in a chain of block and making it 8-bit. So this can be considered as scalability. So modular architecture is one of the example of it. Design a smaller reusable blocks like 4 or 8-bit, then chain them to make them 16, 32, etc. And all is piping and all. No need to learn about it right now. Trade-offs. Okay, Modular design, it has a pros that it can be reusable, easy, and cons are slightly high. It is complex. Then is complex. Paramaterialized HDL. It is flexible. It can be used in mostly all the kind of softwares. I mean processor and all, but same here. Yeah, it needs a complex verification because there can be some mistake many times. Hardware platforms are FPGA, Field Programmable Gate Array, and ASIC, which is Application Specifically Integrated Circuit. Um, it is mostly used by Linux, Spartan, Intel, Cyclone series, etc. We are going to discuss about it more here, like comparison. So reconfigurability, FPGA can be reconfigured as many times because it is used in a testing purpose. While ASIC cannot be reconfigured, it is made in a bulk, so we can configure it only once. Development cost, FPGA has a low cost, as ASIC has a huge cost as we are going to make bulk millions of fabrication. So time to market, okay, it is a fast prototyping and testing. FPGA, while ASIC is slow because FPGA is used to upgrade itself. Every time we can change it, upgrade it, make it better. While ASI we cannot change it and we have to use it only once. Performance wise, it is slow due to routing overhead. ASIC is optimized and faster because we are using ASIC when we have already tested all the possibilities. Then how can we make it best? So it is always optimized and faster version, while FPGA is a slower version because we test again and again and again. So it makes overhead routing overhead. Power efficiency, FPGA consumes a lot power while ASIC is optimized to consume lower power. And best use case, FPGA are used for prototyping, research purpose and all, while ASIC is for mass production, commercial production, software tool like we can use VHDL, Proteus, Logism, etc. Not going in depth. If you want to learn regarding more, I have already provided you PPT, but we should not go in depth regarding it. This is a design of 4-bit ALU. Okay, this is a simpler design. I will show you proper 8-bit ALU working way. Let me just complete it out, then we can go for it. Real world application. Okay. Yes, real world application. It is used in microprocessor, CPU. It can be used in GPU, embedded system, cryptography system, digital signal. All the way it comes because it has a good speed. It is effective. It has good power management. So we are using optimized ALU. Okay. Future enhancement which can be done. So floating point support, AI can be integrated to it to make it better functioning, low power. Yes, we know every time we get a good battery backup with each upgrade. So low power design, reconfigurable ALUs, yes, FPGA, we have all talked regarding it, and optical ALUs, quantum. Conclusion, we have already talked regarding all of this, so I don't think we need to conclude more now. And here are the references if you want to look for some of. Let me show you the socket. This is an 8-bit ALU. Okay, here let me play. Okay, sorry. uh, See, initially it is 0. Okay, let me first teach you all of this. These are two input switch. This is our uh, com, uh, com, so क्या है ना, sorry, complementer. Yes, complementer. This is adder circuit, and this is our 8-bit AND gate, 8-bit OR gate, 8-bit NOT gate, 8-bit NOT gate. This is multiplexer. Yeah, 8. This is our 8-bit multiplexer, and this is our three selecting lines to control the multiplexer. As we have seen the diagram, the controlling line, the similar line are attached to this multiplexer for carry out purpose. This is our zero flag, and here we will get our output. Okay, it is a simple designing. Let us start. If we add 3 to 0, we'll get 3. As you can see, if we add 3 to 3, we'll get 6. 4 plus 2, 6. If I want to do a subtraction, then I will give 0, 0, 1. Okay, then it will subtract and give us 0, and 0 flag will become 1. Okay, it will show that the answer is 0. Now we need to do a let us see ending. 3 ending 3 is 3, simple. Or if I end 1 ending 3, then there will be some issue. Is this ending or not? Okay, this is ending, sorry. That was ORing. Yes, 1 ending 3 is 1 only. And if we do ORing, then 1 ORing 3 is 3 itself. If we do 3 ORing 3, then also it will be 3. Now now we are going for, yes, not A, which is not A, except 3, all are 1. Now not B, let me go for B with 5. This is except 5, everything. Then we will go with what is our A. If I want to know my A, my A is 3. And what is my B? My B is 5. 4 plus 1, 5. 5, simple. And if you want to see carry out, then I'm not going to calculate it out right now, but we can simply just look for it by addition. Look here, using this huge number, then we will get an carry out 2. Okay, so this is a simple 8-bit ALU which you can build on Deeds for Deeds. Thank you.